Okay, we have officially started here and I'll post all this tomorrow. So hope all's going well. I'm going to talk about a couple things, talk about the last exercise. Some things about the last exercise I wanted to mention here is that the basic calculation is new minus old divided by old. Can you have negative numbers?
Yes.
Yes. Okay. You can have negative. Can you have numbers over 100? Yes. Okay, 100% of it. So we have something like the new is 1 and the old is 8. And we got 1 minus 8 divided by 8 equals some sort of negative 7/8, which is like negative 88%. Right? Am I not right? But approximately 88, it went down 88%. Okay, and I just want to make sure we got, because when you run this between years, what did most people do the calculations for, like 2016 and 2017, like I suggested? 2015 and 2016. So you may have some that go from like 1 to 3, and you had a 200% increase, and we're not going to be able to, as Cameron alluded to before, we have something called the small number problem, meaning when we have small, like low values, and we have increases in those, they can only be in large increments with respect to each other. How do we circumvent? And I think one of the questions on the homework was, how do we circumvent the small number problem? Cameron said more data. Where are you going to magically get more data for 2015 and 2016? Oh, I heard something good there. Zoom out. So we just get county level stuff. That's a good idea. What are other things we can do? What are we talking about, Phil?
Smaller quantities. The data for a longer period of time.
Exactly. That's also another thing that I was thinking, where that instead of doing 2015, 2016, let's look at the time period from like 2012 to 2015 versus 2016 to 2019. And so now we kind of, for each of the zip codes, we have this change. There might be some inflection point between 2015, 2016. Maybe with your, did you do any time series analysis with your driving stuff?
We had raw numbers.
Yeah.
They're similar.
Okay. For those of you joining us, or Cameron is submitting a paper on motor vehicle fatalities. So he's looking at the same database that we've been looking at for the last couple of weeks, but he queried out, instead of cancer deaths, he queried out motor vehicle deaths. And then he calculated those by rates at the zip code scale. Is that right? Zip code scale. And he did a little statistical analysis and spatial analysis on all these, which I thought was, I think it's really, it's pretty neat. It's easy to find. And are there spatial patterns with motor vehicle deaths?
I would say so.
Yes. And that's the thing that I find is amazing. That's why we have Geostatistics class. That's why we have geography and GIS, because something as random as you might think of like motor vehicle deaths, where that my chance of having a motor vehicle death is probably the same as every other person in here. And we all live in kind of random areas, but when we look at the patterns on a map, there are spatial patterns attached to those. That's why we're all here, whether it's AIDS mortality or SIDS or ulcerative colitis or any of this other stuff. That's why we're here. And I think it's neat, but it's interesting, and it gets me a job and all those other good things too. So when we start looking at some of this time series analysis, just be careful about working with some of these other small counties. What's another thing that you can do? What are things like county health directors? What do they do with this small number problem? Yes, Chino is done. What do they do? What do we do? A lot of times when they have like deaths less than 5, they'll just no data. just they gray it out and just say, sorry, we can't map it here because we've got small numbers. Okay, and a lot of times when you look at like infant mortality rates for certain counties, for certain demographics, if we look at like infant mortality rates for, say, Jackson County, North Carolina, African American, where there's not a lot of African Americans, it's just gonna say less than 5. Sorry, we can't map it, you know, it could be 1, 2, 3, 4, 5, or 0, or 4. So those are some of the things we've kind of got going on with those. And I want people to think critically and holistically about those, because we're gonna start kind of leaning back on the idea of the mean. We lean back on the idea of the mean when we start doing things like clustering. Clustering is its relationship to the mean. And we started talking about this a little bit with like things like standard deviation, mapping standard deviation. It's dependent upon the mean. So if you have a whole bunch of values in one county that happen to go from like 1 to 10 in 1 year, that's going to tweak your mean incredibly. And that's going to change everything with your clusters and your hotspots and all those other things. So those are some things that we've addressed in the past. Now I'm sharing right now with everyone. Right now we're in week 5. We're going to talk about geographic distribution. So actually we're going to be working with actual maps right now. Now we're going to look at something called the spatial mean, spatial median. Now what do you think the spatial mean is? Well, you add up all the latitudes and blah, blah, total number, and do all that. So, and then we also have weighted spatial mean. These are things that we see every day. You hear about this in Dr. McGinn's class in World Regional Intro to Geography, where we talk about center of mass, center of population, all those other things. And we're going to calculate things, very basic descriptive statistics like center of population for a particular study area. I've got a video posted. We've got an exercise. We're going to start the exercise in class today. I've got some of the book material posted. And then also I've got a reading due in a couple weeks, because next week I am not going to be here. I'm going to be at the NC-AUG meeting. That stands for the ARC Users Conference. And we are hosting a table. I'm bringing a couple students here. So I always like to invite different students to different places and give different opportunities for everyone. So Juan, who's joining us up there in the top right there, he's going. And another graduate student, one's still an undergraduate student, but we're bringing another graduate student with us. And one of the big things, and I'm meeting with my research group next week. So one of the big things we're going to talk about next semester is the schedule. We've got something called the GERS, Graduate and Undergraduate Research Symposium. We have the North Carolina GIS Conference. AUG is really good because these are the people who run GIS in the state of North Carolina. These are all contractors, state officials, all this other good stuff. And then in March, there is going to be the North Carolina GIS Conference, where there's the same people as well as all the people that work for them. So I'll probably go see about half a dozen people that like sat in these rooms and took these classes at some of these meetings here. And that's over in Winston-Salem. I like to make a big push to send as many students as possible. So people that are interested, reach out, because I think like student registration is something ridiculous, like $60 or $50 or whatever. I think Chima submitted. Did you submit something for NCGIS? Oh, it already closed. Yeah. You submitted something for NCGIS. What's that? CDAG closed. I'm not going to that just because I got so many things going on next semester. So Andy submitted something. I submitted something for Andy, so I put my name on it, and Andy will be doing lots of work for that on a project that we're doing on something called hubs, places where we can store data in the cloud. And then next semester, we've got NASA is coming for a visit, since we have a grant with NASA. And then there's something called North Carolina Space Grant Meeting, which is over in Raleigh. So we're kind of coordinating NASA visit with the space grant meeting, so that if you want to do a presentation on NASA related stuff, a lot of times people think this is like space stuff. It's also Earth observation. And so I know someone who's going to be presenting at the NASA thing. So definitely, Michael, you will be submitting something for NASA. And then Andy, hopefully, and a couple other people in support of natural hazard research in North Carolina and the impacts on people. impacts on people. So there's a lot of factors that are attached to that. So those are the things coming up. But next week I will not be here. When I post the announcement for this, you'll see that. You noticed last week I was at like the airport and I set something up really early. And then I got to look at email for like 3 days. So I kind of ignored everyone. But because it was doing some other things. But so next week I'm going to be gone. So the week after, we're going to talk about the midterm. Okay, midterm. I don't want people getting scared. We're going to go through the midterm exam. I'm going to open it up after our break here and look at it. One of the things I do like about midterms is that, it makes you kind of do the work here, so I like all these different assessment techniques because if you're not good at exams, we've got the readings, we've got the exercises, we've got the position papers. I always hated exam classes, which were dependent upon the 3 exams that you had to go and memorize stuff. Another thing about the exams, they're all open note, open book, open everything, just not open person. And so for the face-to-face students, we'll have it during class. For online students, we will post it for a certain period of time. Just make sure you take it on your own. I don't mind people taking it somewhere else while it's open. I really don't. You don't have to come here and take it. Just make sure you take it on your own. If you don't, I might find out, I might not. It's really bad if I do find out. That's not fun. That's not a fun conversation to have. And if you do take it on your own with someone and I don't find out, that's cool. You got one over on me, but it's going to be found out at some point in time, whether you're in the workforce or whatever. And so, you can lie to Mulrooney or whatever, but, make sure you know stuff. That's that's the big important thing. Don't cheat yourself. And I just want to encapsulate all the geostatistics so that we can go and make charts and graphs and put powerful visuals into papers like you with my name on it or submitting in the near future to make powerful graphics and visual that'll support the kind of plethora of data that exists out there. And so I'll talk about that when we're done. I've got a map. I've got some tabular data. You can probably guess the questions we're going to be. So I'll go through some of the questions. I might change them this week if I kind of get motivated. I might just do the same. I don't know. It depends on my level of motivation to change them, but we'll look at the exam. Open note, open book, open anything. Just make sure it's taken on your own, and I'll post explicit directions for those in the future. So today we're going to talk about measuring descriptive statistics. So today's exercise is actually going to be utilizing some of the GIS. And the reason why we have some of these is some of the problems with measuring density. There's a lot of problems with measuring density, but on the left here, we're looking at a map of Winston-Salem for assaults for every 1,000 people, robberies for every 1,000 people. So these are nice, I don't want to say pretty maps, but visually appealing maps, which use kind of good colors right here. Not good colors, but good color scale. I've got the legends right here. The previous versions of ArcGIS, which was called ArcMap, to me, they were a lot better at making maps than the current iteration of ArcGIS Pro, because ArcGIS Pro is not built, but it's largely built for putting stuff on the web so that you can look it on your, look it on your phone, tablets, or whatever, zoom in, zoom out. So the ideas of projection get a little bit skewed when we're working in ArcGIS Pro, because you can kind of, move your finger a little bit and you can change scale, where these are all at a dedicated scale. Now, what are some of the challenges in working with assaults versus robberies? Can we add up the number of assaults plus the number of robberies or anything like that? You can, but we're working with a different scale. We're here working with 0 to 142, and then let's look at 0 up to 22.57 assaults. So it's really, we're comparing apples and oranges when we look at these here. And some of the things we looked at last week, where we were looking at crime rates, where here, this is in 2005 Winston-Salem, this is 2007 Winston-Salem, when they annexed a bunch of land. And I talked about this last week a little bit. Where that now we're starting to collect data for these places right here, and these places in the northwest corner for Winston-Salem that we didn't collect previously. So how do we do this change detection? So when we measure problems, and there's problems with measuring density, and we're gonna spend a whole class, and whole class at the end of the semester talking about circumventing issues around measuring geostatistics. And this mean small number problem is one of those. Large number problem is one of those where if you have just one cancer death and 4 people live in the zip code, it doesn't mean 25% of the people have died of cancer, or you have a 25% chance of dying, which is going to skew your mean, do lots of other things with your hot spots and your cold spots, which are basically just calculations. They're just calculations. So the extensive study areas and the shapes of enumerations change from one time period to another. Those of you who've ever worked with census data can understand some of the challenges where that census tracts break up from time to time. Even counties from time to time either change names, get new zip codes, or get consolidated. Now, different types of density phenomena cannot be compared, so it's difficult to run descriptive metrics, pattern analysis, clustering those when we're comparing apples to oranges. And so, like we talked about before, I found this is neat because these are like real world applications where we can run some of this, not only change detection, but we can run these descriptive statistics. So we're going to look at the math behind these. Most of you notice I like to put these formulas up there. And even like we did with spatial interpolation, I was working with a group previously where we did some spatial interpolation. It's just basically a big weighted average. I don't want to write formulas up there and you memorize them, but I want us to kind of click a little button and make sure, hey, this looks right, this doesn't look right, this looks right, and make sure what these things look like. And so the city of Winston-Salem annexed about 19,000 new people. You can see these areas in yellow were basically the areas that were annexed in 2006, I think it was. And so you can see the boundaries in 2005, the boundaries in 2007. Some of the major challenges in that these areas in yellow, they didn't collect crime data for previously, but then they all of a sudden started collecting crime data for these. So that when someone in these yellow areas calls 911, Durham Police Department instead of Forsyth County Sheriff's Department shows up. They use entirely different reporting systems and all those other things for Forsyth County as well. So we have spatial statistics, and today when we started looking at some of the spatial tools with our other class, is that when we open up the toolbox, there's probably like 30 different toolboxes, and you've got dozens of different tools within each of these. And I've probably used, I don't know, maybe a third, a half of the toolboxes and the tools. And so I really want people to figure out how to use the help and figure out what each of these things do. They're always adding new things to geostatistics, and I think someone like Chima, who's kind of up to date, who's up to date on the geostatistics portion of things, can probably speak a lot better than I can to some of these geostatistics. But the thing about spatial statistics, what we're talking about, is that they're not like traditional aspatial, non-spatial statistics, meaning mean, median, mode, range, z-scores, standard deviation, and variance. Those are some of the descriptive metrics. Now, descriptive refers to describing an entire data set where that a local metric is assigned to a particular enumeration unit or a record. And so each county will get a z-score, but the entire data set will get a variance, a mean, mode, range, standard deviation. But each county will get a z-score. So the z-score for Durham County is going to be this, versus the z-score for this county, for this particular metric right here. Methods that use distance, space, and spatial relationships as part of the math for the computations. We just run into so many issues when I talk about distance. What's the word distance mean? We're going to talk about all the different words of the word distance. Just like some of the rabbit holes that we've gone down with our food desert research. When I use the word food desert research, how close is it? How do you measure close? What is close to what? How far is what to what? My house, if I, think about how many calculations would I have to do if I were to measure it from everyone's house to the nearest supermarket? It's a lot of calculations. How do you calculate that? We do this in our phone pretty easily, right? I can just type in supermarket, hit the little button and do that, but try to do it 200,000 times for the entire county. It's take a while. Everyone in the county typing in nearest supermarket and then figuring out how to do this. So the idea of distance and proximity takes on a new extent. Yes. Okay.
I'm sorry.
Okay, all right. So it's the spatial distribution and pattern analysis tool. So basically, we're trying to view these on a map. We identify characteristics of distribution. We measure geographic distributions, and then we analyze patterns and map clusters. Okay. And after the midterm, we're going to start looking at things called inferential statistics. That's a big fancy word for just saying, how close is it to random? Because what's random mean? You got highs next to lows next to median. It looks like a checkerboard. You know, there's sometimes highs next to highs, you know, in random patterns, you know, it's random. But what are the chances in inferential statistics that we have five highs right around each other? Really low. And we do these with degrees of confidence or confidence intervals. So we talk about 90, 95, 99% confidence. And these statistics, we mainly deal with points, lines, and polygons. What we were doing today with another group is we were doing spatial interpolation routines where we were creating PM surfaces for the entire state based on 22 values throughout the entire state. And so some are good, some aren't good. There's other statistical tools that we can use to describe these. So the use of spatial statistics is to assess patterns, trends, relationships. Today, we're going to talk about descriptive statistics. That's it. Spatial mean, spatial median, spatial mode. I think I got a paper posted somewhere about those. So we can better understand geographic phenomena, maybe pinpoint causes of specific patterns, and make decisions with high levels of confidence to summarize the distribution of a particular number. And so we're going to be kind of focusing right here, because after the break, we're going to be looking at something called quadrant analysis and Poisson distributions. All it means is that how close is it to random? That's all inferential statistics are. How close is it to random? You know, I have all these crimes right here. This is a hotspot. What are the chances that all those happen to be near each other compared to random? You know, I think people get a lot of times scared of these things, and that's the best way that I express these. And I've got a couple of go-to tools that I love to use. You know, Lamana, who's joining us online, knows my two-tailed t-test, you know, and I love my two-tailed t-test because someone suggested it, you know, 10 years ago, and I'm going to stick with that. I'm going to stick with the clusters. You know, I'm going to stick with a little bit of correlation, and we're going to talk about correlative statistics to see what relationship does one impact the other. We have dependent variables and independent variables. And what are all the independent variables that impact a dependent variable? Those get a little wonky as well because, you know, you don't want, we start to bring out the word like heteroscedasticity and multicollinearity, and they're just big fancy words, ways of saying, you know, these relationships might be skewed based on your input data. So when we talk about geographic distributions, what are some areas where we want to use basic descriptive statistics? We're just describing the entire data set. Where's the geographic center of phenomena compared to the center of an enumeration? And that's what we're going to do today for an area around Greensboro, where we're going to look at deer vehicle collisions versus the center of population. Are they in the center? How are spatial data skewing the phenomena in one direction or another? Now, when we measure distance, we've got lots of ways to measure distance. One of them is Euclidean distance, meaning straight line distance, meaning profile distance. They're really easy to calculate. The one thing about spatial statistics, they typically use Euclidean distance. Now, Euclidean distance might be practical when we're working with PM. You know, particulate matter, because particulate matter doesn't need to take a road, right? It's kind of a phenomenon that's close. But profile distance, is that practical when I'm driving somewhere? No. A lot of times when I type in my phone, I type in my address, it'll tell me how far it is. It'll say like 53 miles. Then it'll say, oh, it's really 67 miles when you drive on the road. So it calculates the X and the Y, the latitude and longitude, and then it figures out what we call network distance. So this network distance Networks are examples of roads, but they can be like sewers. We have a student, he sat right here, he made that poster right there. You'll see him at the NCGIS conference. I might even see him next week at the ARC Users Conference. He does all the sewer mapping for, stormwater mapping for the city of Durham. Lives over in Snow Camp, over in Alamance County, and that's what he's been doing since 2018, 2019. Came here as a transfer student from Alamance Community College. That's all he does is not network, road network, sewer network. Because the sewers have to be connected at somewhere. They end at your house and then they connect somewhere to something bigger, 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 bigger. We have Manhattan distance, which is measured along right angles. As you can imagine, like, city of Manhattan or New York. In Manhattan, you can just go left, right, unless you go down Broadway or something like that. And then we have network distance, which follows pathways, waterways, and you typically see these map quests in Google Maps and all these other things. Now, the thing about Euclidean distance, they're really easy to calculate. And so I kind of pulled this from my new book that I really like, but it's just the square root of delta x squared plus delta y squared. Also, this delta x, delta y, square root of, this is just a calculation, x1 minus x2 squared plus. That's what we call it. Remember this from geometry class or whatever. This is really easy to calculate. Network distance. So we can just calculate the difference, difference between the x's, square, add it up to the difference between y's, square, and square root of the whole other thing, whole other thing here. This kind of looks like what? Your Pythagorean theorem as well. It looks a lot like Pythagorean theorem. So we got the distance formula right here. We can calculate this. A lot of times in the world of GIS, we just kind of flatten the map right here, put it into feet. And so the reason why we use things like North Carolina State Plain is because we flatten the map, we stick a 0 point somewhere down in Alabama, and then now we can just measure it in feet, but instead of things like 1,3, 7,8, this is 1,203,000, 457,000 on a flat surface, which is basically representing the real world. Does the same exact thing. That's why we like this North Carolina State Plain, as opposed to geographic, where we got to do the sines, cosines, tangents, and convert all that stuff. And we saw some of those things when we were working. I was working with a group right before, where that E0 point, all that stuff. That's like 0.002 degrees, and now we got to go through and convert those things to miles, which are going to change depending upon your latitude. Because you go further north, your degrees of longitude get smaller and smaller. Now, these are some examples that we have here. We got a student, the poster used to be back there, but we got a student here. She was looking at large supermarkets, convenience stores, vegetable markets. The one challenge about measuring these is we want to see which one of these had the most amount of clustering. And this will get into what we'll talk about in a couple of weeks here when we look at Poisson distribution and the Kondramarov-Smirnov test. And I'm just going to mention that, but it just measures how close it is to random. That's all it is with the inferential statistics. But when we look at large supermarkets versus convenience stores versus vegetable markets, some of the challenges that we have are just by looking at it with our eyes, it's hard to tell which one of these is most clustered and least clustered. What's the word clustered mean? Two together, how close they are together. Because I can see some over here, and I can see some over here, but we're going to talk about ways in 2 weeks to measure, how do we measure clustering? Right? We have something called nearest neighbor analysis, and then we'll talk about quadrant analysis as well. Because when we look at spatial distribution, we see random, we see uniform dispersed, and we see clustered. Now, clustered and dispersed, there's intentionality with these here. So that random is likely to occur at any location. So we might have high values over here. We have a low, we have highs, we have lows, kind of all dispersed, not dispersed, but all, I don't want to use the word dispersed, with something else, but all just scattered throughout, where some highs next to lows or whatever, where that there's intentionality that exists with the uniform or dispersed pattern as well as clustered. Meaning, we look at income right here, income doesn't look like this. And most phenomena, the reason why I have a job doing GIS is because most phenomena out there, whether it's ADHD or AIDS or suicide or motor vehicle collisions, is that they're probably this. You can see patterns of clustering. In some cases, we just see uniform or dispersed. Now, what are phenomena out there that are dispersed? What are phenomena out there that are intentionally made to be far away from each other? What are phenomena that you would want to put out there or that you would expect to be far away from each other? It's a tough one. Or far enough away from each other. I'm building a McDonald's. Do I want to build one McDonald's right next to the other? No. It needs to be far away enough from the other McDonald's so that it doesn't compete with each other. Now, McDonald's, they're relatively small. There's probably, 8 McDonald's in Greensboro where I live. But what about Lowe's? How many Lowe's do you think are, in Greensboro? Probably 2. You don't want to put them next to each other. You want to put them as far away from each other, but as accessible to the people that are going to shop at Lowe's, and as well as accounting for zoning, cost of, costs and the cost to buy the land and develop the land and all that other stuff as well. Other things like cell towers. You don't want 2 cell towers right next to each other that are owned by the same, company or telecommunications provider because they're basically providing service to the same exact area. So things like cell towers. So we have phenomena that are intentionally made to be dispersed. What about call boxes? And in a couple of weeks, we want call boxes. And this is what Michael did for field mapping class, where he went and collected all the call boxes around campus. You think they're clustered? And I haven't figured it out yet, but we're going to be using your data in the exercise, but we're going to see if they're clustered. That'd be really bad if they're all clustered in like the same place. In theory, they should be probably somewhat uniform. It's kind of a combination between uniform and clustered, meaning there should probably be more of them around the dorms as opposed to other places where there's more students. But I don't know. I'm kind of interested to see what it's going to look like. But I would definitely hope they're not random. That'd be tough. Okay. But uniform is far away, they're likely to be distant, and then cluster, where that every point is as close to other points likely to be close. So typically, when we start looking at a continuum of spatial distribution, we go from uniform to random to cluster, where random's kind of somewhere in the middle, where there's intentionality that exists between the dispersed and the clustered, albeit for different reasons here. So we could look at examples here of spatially clustered data. This is kind of raster data, some of the data that we were working with today, but instead of looking at numerical PM data, this is categorical data. This might be landslide incidence probability or something like that, where that's something that would be geographically random would be, you might have some reds next to light greens next to dark reds or whatever. So we have geographically random versus spatially clustered. So this is what we mean by these. And so when we start to look at inferential statistics, essentially we're trying to figure out, are there things clustered? Are there things random? And, we've got Lamana on here, and she's going to be presenting at the TRB, Transportation Research Board annual meeting in early January. And we did the same thing for motor vehicle thefts around campus. You bet, there's clustering patterns attached to motor vehicle thefts in Durham. They're really, really high around here. And we can probably look at that paper at some point in time. Now, why do processes differ from random? Okay, that's the big thing, because you know what? At the end of the day, I'm the where person. I'm not the why person. So when Cameron writes that paper on motor vehicle thefts, we can do the where, I can do the where all day long, but at the end of the day, what do people really care about or want to look at? They want to look at why. Why do health patterns exist in the certain? Why are there motor vehicle thefts a lot, or motor vehicle deaths a lot higher in the southeastern part of the state, southeastern part of the state? What is it? They're younger, they're probably younger drivers, but also, what about the roads, what about the lighting, what about the enforcement, all these other factors that are both natural and kind of anthropogenic. Disease clustered because people cluster, So processes differ from random in two primary ways, meaning disease cluster because people cluster, such as cancer. And a lot of times, in this day and age, people die of stuff that accumulates over a period of time. I'm just not walking along and I just, drop dead. Okay, it's things over a period of time, whether it's cancer. Now, what causes cancer? It could be, biological, but it's usually exposure to food or certain triggers, I guess, food, air, whatever else triggers this. I got a friend, he did research, he's a doctor, so he did a lot of research on this. And so what are certain foods, air, water, junk, and, junk that you eat, red dye, all that other kind of garbage out there that we're still trying to figure out the causes to these things, cause these. And then also cancer cases cluster because potential sources of cancer, like chemical plants, cluster. I won't talk about the second order effects, but the first order effect is that there's interdependence of the points between themselves, meaning basically, geography is kind of the ultimate, is the ultimate variable that we have here. Disease is clustered because people catch them from others who have disease. So if you kind of live by yourself and we're never around anyone, what are your chances of getting a disease? They're really, really small. And I think the interesting phenomenon when we start looking at motor vehicle thefts, AIDS, or suicide, phenomena that really aren't person to person. Because at the end of the day, when we start looking at things like COVID or, Ebola or what was it, the Asian bird flu, this is like 20 years ago. It's a question of geography. You can see it goes from like China to Toronto to New York because there are people in close proximity to each other. To me, when we start looking at like bank robberies, here's the cluster of bank robberies right here. We might have a lot of bank robberies here. We might not have any bank robberies here because there's no banks. So those are some of the things to kind of think about, kind of some of these kind of note-up questions when we start looking at the small number problem, change detection analysis, normalization as well. And so mapping bank, bank robberies, well, they only occur here because there's only banks there. And we're not going to have bank robberies in other places where there aren't banks. So those are things to be aware of when you start kind of talking about results and all those other things. Now we're going to talk about the statistics and we're going to calculate these. One of these things, the center. I talk about things like distance, and there's three different ways to measure distance. When we start doing like food availability, when we start talking about food availability for our food desert stuff, like there's so many different ways to measure availability, food access, and density, and how far. Because it's pretty easy to do Euclidean distance, but Euclidean distance really isn't practical. And imagine doing that from my individual house to all the nearest thing. You're talking about thousands and thousands of calculations per second. Speaking of which, I just bought a new supercomputer. I don't know how super it is, but it's in my office there, and hopefully it'll be able to run lots of new stuff. So we're gonna get Daniel checking it out and all that other good stuff, and see if it's any good. I don't know. Is it any good? Is that laptop any good?
Yeah.
What's that? Oh, okay. Is it good or it just gets the job done? Hey, did I give Andy one too?
Yeah.
Is that yours? Is that it might be the same one, right? That one's better? I don't think I really well, we got a new one. It's got like 5 terabytes, and I got the fastest it can run. But so we can run these calculations. I don't mean to talk about the computer, but so we can run these calculations, because as you can imagine, running all these network calculations from my house to every single nearest grocery store, it takes up a lot of space. Even when you run your calculation here on your phone, how long does it take? It takes a couple seconds for it to pop up, because it's like, all right, I got to get myself to the nearest highway, get the highway over kind of where I'm going, and then do all the calculations. So it's probably doing a couple thousand calculations per second, and then kind of coming in without knowing anything for thousands of calculations. We're looking at billions or trillions of calculations to do this. So when we talk about where is the center, we have something called the mean center. All it is computes the average X and Y coordinates of all features. That's all it does. And so I can put the little formulas with, the sigma notation, and I always give those in stats classes and math classes, because to me, they weren't practical. But if I have a whole bunch of latitudes of prime, so your spatial mean, your X, and then there's the average, is just X1, X2, 3, X4, divided by N. So that is your longitude, and then the latitude is plus 1, plus 2, plus 3, plus 4, divided by N. So there's two separate calculations. So when we do the mean, what do? Of all the test scores, your test score plus your test score plus your test score plus your test score, add them all up and divide by the total number of test scores and the number of people taking the test. Now, the spatial mean, it's a little different, because when we talk about your location, you not only have an X, you got a Y. So your X plus your X plus your X plus your X plus your X divided by that to be one component. And then so we got your longitude, which is your X, and the latitude, which is going to be our Y. Because here, we're going to do something a little different with the weighted mean. We're going to do the same exact thing here, but we're going to let the computer do it. Like, we're not going to do any, hand jam calculations or anything like that. We will not do that. So we have the mean population center of the United States. So what we have here is, whenever we have the census, they take the mean population center of the United States. So in theory, this point down here, half the people live north, half the people live south, half the people live east, half the people live west. And you can see where it was in 1790 over near Chesterton, Maryland, and it's kind of migrated to the west and to the south. Why is it moving to the west and the south? What's that? Where are people moving? To the west and the south. To the west and the south. At one point in time, half the people in the United States lived east at this point, north of this point, and then now we're kind of in the middle of Missouri right here. Now this is going to be a weighted average, so we'll talk about what this weighted average is, but this weighted average is we're going to add in population divided by the sum of the population. So instead of weighting by the number of credits, we're going to weight it by the population of it. Okay, so the population of this county plus the population of this county, we're going to weight it. Just like we do with equality points and all that other good stuff there. And we're going to let GIS take care of this for us. So we're going to let GIS do this for us. We just notice, and we're going to open it up like, hey, this looks weird. Should be somewhere in the middle. So we open up the data set, it should be somewhere in the middle. So we have something called the spatial mean, which is just the average of all the X and Y's. Other centrality metrics, we have spatial median, which is the median of the X and Y. We have something called the center of minimum distance. Sometimes the spatial median and the center of minimum distance are the same thing, but basically it is a point where it's minimized the distance to every other point. So it goes through another calculation where that the distance between this point and every other point will be minimized. But if you stick it in the corner somewhere, it goes, if you stick a point down here, calculate the distance, it's really far to everything. You stick it in the middle, it'll minimize the distance. I want to articulate that because in a couple of weeks, we're gonna be doing something called nearest neighbor analysis, where it just calculates how far is something to its nearest neighbor, and then just add up all the numbers and divide by the total and see how it compares to a random distribution. We also have something that is called the central feature. The feature that is in the center, closest to the center. It's typically the set feature that's closest to the center of minimum distance. So even when we talk about center, we've got like 4 different definitions of center. I want to make sure we just kind of understand this. Here is the formulas. Basically, add them all up and divide by the total number. When we have the weighted, it's just the weight times the value divided by the sum of the weights divided by the total population. Next, instead of divided by n, we divide by the total population. And then total also calculates third dimension. Okay, so when we look at location coordinates here, we have an x and a y. If we just add all those up, the average is 3.81, 2.51. I just want to make sure we know how to kind of calculate this. Just add them all up, divide by the total number right here. And so the mean center will be 3.81, 2.51. Just by adding them up, adding these up. Really easy to calculate. Same exact thing here. Okay, we got all these points. This is the mean center. Just averaging up all the x's, averaging up all the y's. So we get a brand new x, a brand new y, which is going to be the coordinate for it. Okay. We have a tool here called mean center. After the break, we're going to work with mean center. Okay. And then we have a weight field. So what do you think the weight's going to be? I do a little drop down. My weight's going to be population. And guess what? You just got to make sure you got population at the appropriate scale. And so we're going to be doing weighted means, because a lot of times when we look at areas, do we want to put it in the center or do we want to put it where the people are? We want to put it where the people are. Then we can look at purchase patterns and all that other stuff. And so we can look at the weighted mean on all these as well. So like the weighted mean of population, this is Rockingham, Guilford, this is where Greensboro is, Forsyth and Stokes County. The center of population is over here. Why? Because more people live over here than live in these other 3 places. So this is a real kind of basic calculation. The median center, the center that minimizes the overall Euclidean distance to the features. To me, it's one and the same. So it's another centrality metric. That's all it is. Like mean versus median. Okay. I have lots of neat explanations for these things. And so I'll kind of ask folks when we look at this, we can click on how does the median center work. We'll see these nice little formulas right there. We can look at those if you want to explain these. More importantly, what you can do is you can like cut and paste all these into a paper. And guess what? You've got your introduction, you got your methods, and guess what? You got people who tell you who did the original research, so they already do the research for you. And so a lot of times when you write a paper, like let other people do your research. Guess what? These two, they already did the research on the median center. So if you write a paper on median center of crime in Durham, these people have already done it. Now, you go do a little bit of your thing, but take a look at all the resources available. That's kind of why I stress on the quizzes. That's why they're open note, open book. You know, doctor isn't going to close your book and say, all right, I think you've got this. You know, they're not. They're going to utilize every resource available, whether it's internet, videos. Now, if you didn't look at any of the videos and you haven't read the book, then you don't know those resources exist. So take advantage of all the resources available to you. You know, Google might help, but if you type in the word median center, it might know something, it might not. You type in the word resolution, there's a lot of definitions of the word resolution. So make sure you know how these are applied, because this is going to go by real quick. We have the central feature. Which one is closest to the median center? And so we've got all these like total distance calculations, all this stuff. I just want to kind of calculate this because when I was a kid, I used to love looking at maps. I have a paper, the paper maps and the atlases. And at the beginning of it, they had like a big kind of graph that looked like this. So how far is it from like El Paso to Albuquerque? And then I can look at El Paso to like Boston and figure out which one's the furthest and the shortest and whatever. And so we've got these kind of graphs that look like this. And so from A to B, it's 2.59. From A to C, it's 1.93. From A to D, it's 1.64. One of the neat things in our network analysis is that we can calculate graphs that look like this. I think these are called like TD matrices. I'm looking at Chima or Andy or someone. Does that ring a bell? Like OD matrices, origin destination matrices. And so you can create things like this. We create things like this, which pretty neat, We're really neat. I used this one time to help do the football playoffs, because a lot of times the football playoffs, you got teams going from like Greensboro to Charlotte or whatever, first round game. So kind of group all the teams together before they moved. So I really crushed my computer kind of doing all these calculations for 32 different teams and then looking at the permutations. It got really ugly. So we got the mean center right here. So I'm kind of circling back to the mean center right here. And then other things, we've got spatial distributions, we got spider diagrams. There's other GIS software out there besides Esri. We have the other thing we have is called spatial distribution. This is called the standard deviation ellipse. And so we have 1 and 2 standard deviation ellipses where the center is the mean center, and then standard deviation. What's the definition of a standard deviation? Let's get deep real quick. What is a standard deviation? Can you tell me in words what standard deviation is? How far away it is from the mean. In a normal distribution, approximately how many points or data points are within 1 standard deviation of the mean? About 65, 66 in a nice normal distribution. So these ellipses are created mathematically so that about 65, 66% of the points are in here within 2 standard deviations. What is it, 95%, something like that? 95% are within 2 standard deviations. And so I can look at the distribution of points. So if I look at certain crimes where hey, this ellipse, remember that ellipse stuff from math class? What is it? A over 1 over A squared plus 1 over C squared. I forget what it is. Remember the formulas for all that stuff? I don't want to remember it either. I don't. But the calculation for an ellipse here, it goes through and calculates it. So it's got a longer axis this way as opposed to this way. But if we look at certain crimes where if it's got bigger standard deviation ellipse, what does it tell you? If one set of points has a larger standard deviation ellipse than another. It's more what? Exactly, it's more spread out. It's more spread out versus less spread out, which is concentrated. So these are basic descriptive metrics that we can use. We're not using big fancy words like inferential or correlation or anything like that. And so I really want to make sure we so about 68 versus 95. Here are the formulas right here. So, I can start to figure this stuff out here, here. But this is how we calculate the standard deviation ellipse. So the results. Some of the things that I've done previously was I created standard deviation ellipse for potential wind power sites in Western North Carolina. And so you can see where they're I think they were flat. I used a whole bunch of criteria from the National Renewable Energy Laboratory. And so you can see where they're kind of concentrated right here, and then how close they are to populated areas. I want to circle back to what we did last week. Remember I was talking about change detection? Now, hopefully this will make sense where that annexed area in Winston-Salem in 2005 to 2007, the center of population moved to the north. So it gobbled up more people in the north than the south, but then all the crime moved to the south. So when I got all the new points kind of had a south move to the south with spatial mean, spatial median, center of minimum distance, all moved to the south. What's that tell you? We're gobbling more people in the north. We're taking up more crime in the south. Very descriptive statistics. Now, I don't know exactly where. We can use, we can group this stuff by census tract or zip code or whatever. And then we did the same exact thing here for part 2 crimes, meaning less serious crimes. Moved to the north, population moved to the north, crime moved to the south. Because a lot of times, how many crimes occur in Winston-Salem? It's like 50,000 crimes that occur. So it's difficult for me to look at my eye and say, yeah, I can see more crimes in the south than there are in the north. What do 50,000 crimes look like? Just a bunch of dots on a map. They really do. And so it's your job to make sense of these. And these are some of the tools that we have of these. We'll come back at 6:10 right here. But what we're going to do is we're just going to open up exercise 4. If we, I'll open up the exam too. And so the exam will be taken in 2 weeks. But we'll open up the exam, look at that, and then we'll start working on exercise 4, kind of talk about some of the tools that you have available to you to do some basic descriptive statistics of the area, and we'll do those together. So I'll see you all in about 12 minutes. What's up? How's it going?
Good. Sorry I was late. My daughter told me to give you this.
Oh.
Because she knew I was gonna be late.
Thank you. Is she in high school?
Yeah.
Oh, is she doing good?
Yeah.
All right, where's she go?
DSA.
Europe School of the Arts?
Yeah.
Okay.
Loves it. She's doing pretty good.
Okay.
She told me she's gonna be in the Navy when she graduates.
Oh, I had a kid in the Navy, so that's cool. Yeah, he's lived in Hawaii like the last 3 years, and I think
Really?
he's coming back to Annapolis, Maryland.
Oh, cool.
So I think he decided to stay in, and he's off the payroll. We don't have to worry about him, and it's good.
I don't know what she's got here. She wants to join the Navy first and then go to college.
Good.
So she was thinking about going to college first and then join the Navy, but she said, I'll get money for college. So
Yeah.
I'm gonna join the Navy first.
Nothing wrong with that. And you go there and you're a little more, even my wife just went and did 3 years and then went and lived her life. So,
For sure. Yeah,
Yeah.
That's what I'm hoping because she's like a crazy teenager. Right
oh, I
now.
know.
She's got her own opinion.
Oh,
and she's-
oh, I have kids who are very opinionated.
Oh, God.
And
It's like, oh, I see where I know where you get it from, but man.
tough to fight. Yeah.
I'm not gonna tell you. I'm not. I told you, and I'm not gonna fuss with you. I'm just gonna be like, okay.
They get to a point in time, we call it banging your head against the wall. If you want to bang your head against the wall, go ahead.
That's how I decided. Okay, that's fine. Okay.
That's fine. Just don't spend any of my money on it.
Yeah, yeah.
But I think our son, he got married and he's responsible and he's like, he wasn't the kid I knew who was having trouble, passing classes and getting calls from teachers. He's a role model where he works and we're really, really happy, he's kind of got his own life and doing his own thing and it's good. And, I don't want to thank the Navy, all the way, but he did some growing up and he got some structure and he can't say, no, I don't want to go to school today. I'm going to be late. And
Yeah.
they don't like late in the Navy. So she's got to deal with and he went to boot camp in Chicago and he got really lucky because he played the trombone really well. So he got to play in like the band during boot camp. So he'd do like all the graduation. So while they, the other.
Me about that. And I told her, because when I went into the Air Force, that's what they said, if anybody with any musical talent.
Yeah.
you go over here in this line, and then
Yeah.
everybody else, you go over there, and then they test you, they give me the answer, they test you.
Yeah.
How well you do, craft, then they send.
They
it
send
to
it back,
regular.
And so, it didn't help too much, but it helped him stand out in the pot in a good way. And I think the thing with him in boot camp is, don't take any of this stuff personally, you know how it was. They yell and scream and they wanna, do whatever, and you just don't take it personally, just say yes, sir, no, ma'am, and, move
And then
up.
they tell you, why are you calling me sir? Why are you calling me ma'am? I'm not an officer. I work for a living.
Yeah,
I got that a lot.
okay.
Cause it was just like,
You couldn't do anything right.
no, ma'am. Yeah, nothing you did was correct. And they wanted that. They wanted you to not just do it off road. They wanted you to be present in your mind.
Yeah,
Don't just say it, understand what you're saying. Be there. Don't
Yeah.
just say something because you think it's right. Think
yeah.
that's what they were trying to beat into my head.
Oh,
I
man.
don't know if it works. So, almost didn't show up.
Oh, okay.
Dr. Chapa has no class tomorrow. He got a convention.
Who's there?
Dr. Chapa,
Oh, Tapa, yeah.
he's at a convention tomorrow,
Okay,
and you are at a convention next week.
yeah.
And I was like, is it all in the same week or is it?
No,
No, it's not.
no.
And I was like, I don't think we have class today.
Oh, he teaches that class?
And I'm like, oh, I'm supposed to live this year.
Okay,
Yeah.
cool. Is he good? I like him.
He's nice.
Okay. Okay,
I've had to Google some things after.
okay,
Because I don't know anything about seismology.
okay.
And I was focusing on a lot of seismology data in the start.
Oh, good. All right, cool.
Because I'm not familiar with it.
Yeah. Well, yeah, that's one of the core classes for this program, so make sure.
It's fun. Interesting to learn, but yeah, I had to. Learning something. But it did, yeah, but I've learned some of it.
It's good.
It's, I finished the homework and I was about to. Once it's just. Oh, I'm back.
Just take a picture of your phone and
I know, right?
convert it to a PDF, so that's what I did. So.
Yeah.
I'm gonna take a quick walk here. I got a computer I just bought, so
Oh, yeah, I agree.
I'm excited. All right, this thing works for you and stuff. All right, cool. You get GIS installed on here? Then I don't think I have too much space, but I don't know space.
Well, yeah, I think one rest.
I hate. All right, we got Daniel taken care of. Oh, yes.
So. Good. Yes. I can also buy one. Yeah. Let's see. Yeah. Yeah. See. So that's like. This one. So like, what's it's what's shit. You know, shit. I said, no, no, I'm already checked out. Right, focus now. It's bad in the place. Is it really all in? Should we? That's a hard one. Yeah. Yes. This is second. So. I'm sure. Yeah. 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 Sense of this. This is getting deep. Because it's been. But actually, she was on. Yeah, that's something. So, same. Yeah, yeah. Not because of yeah. She it's very. No, that has gone out yet. Not surprising.
Stop. Oh, no, that's, all right, that's hard.
Okay, we're back here. All right, and so this is for everyone who's kind of joining us asynchronously as well. So we're sitting here in week 4. While we're kind of sitting here, we're going to open up this assignment here. And in the meantime, we're going to go over the exam here. When you open this up, make sure you unzip it. That's important. We still have some people that aren't unzipping it. We've got lots of file points, lines, polygons, APX files, all these other things. So when we unzip it, you'll see deer vehicle collisions, week 5 counties, block group, study area, blocks. So these are the actual blocks which compose data. We'll explain some of these here because I like to show a lot of data at different scales. And for your projects, feel free to utilize like all the data that we have in this class. But at some point in time, and some of the people that we're working with in our rotation, is that like you're starting to make your own data. Like you got to make your own data from scratch. Cameron did a really good job of it with the motor vehicle depths, but you had to outline the zip codes, right, that we used from some class, and then you just joined it to that. You just joined it to that, and I don't think did you do any like socio-economic relation? Yeah, who and where, basically. And I bet you there's probably some, impacts of maybe race or socioeconomics or something like that that can be above and beyond. That might be a good position paper for this class if you think about it. Is that what you're thinking about for the position paper? Oh, okay. Oh, you're an undergrad. You taking this as an undergrad, so you don't even need to do the position. Okay, so just get you done with. Okay, so we're gonna open that up. But in the interim here, next week or in 2 weeks, we're gonna be taking the midterm. This is the midterm right here. I want to make sure everyone can see what it looks like. So I've got a map for the midterm exam. I've got tabular data for the midterm exam again itself. What do you think you should do when you see these things? Probably open them up. Okay, feel free to download those now and have these ready to go. And so I can download these. Cool. Kind of like, I'm kind of doing this the first time. Yeah. Okay, so midterm and exam table. What do I got here? I think I have these kind of filled out so you can just kind of submit these on your own here. Okay, cool. All right, so Z-scores. All right, for Durham County, Forsyth County, Allegheny County for median age and average family size. Okay, so right off the top of my head here, we got average family size and median age. Those are going to be normalized data. Just thinking about it, these are normalized data. So when we fill in these Z-scores, even before I even calculate anything, what's a good Z-score? Can I get 87 as a Z-score? No. What about -1? Yeah. So somewhere between like -3 and 3. So those are things that make sense. They get a little wonky when you work with data that's skewed, like population, but median age and average family size are going to be display a normal distribution because they're normalized data. Football wins, okay. Vikings and Nighthawks. County population, okay. Population, median household income, okay, all right, interesting. And then we got swine lagoons. So number of swine lagoon density. Okay, so get an idea of what we're looking at here. So I guess we're gonna have to probably count the number of swine lagoons in Duplin County, Nash County, and Forsyth County and calculate the density of those. And so maybe in 2 weeks, I might change the names of those counties like next week or something. I don't think I will, but maybe I'll change the questions or something like that. But Duplin, Nash, and Forsyth County. So get the idea of what we're kind of thinking out, looking at right here. And then while we're here, we'll download the APRX file. And a lot of this is just have an idea of what a good answer looks like, what a right answer looks like, how am I going to calculate these? And then while we're here, we'll get the map here. We'll download the map and then make sure we unzip it. So this is where this stores mine here. Midterm map. Make sure when I click on that zip file, if it says extract all, what do I need to do first? Extract all. All right, does it say extract all here? Nope, so I'm ready to go. And then this is the midterm exam map. Probably got something with swine lagoons, right? And this was part of a project that a student did a couple of years ago. He's actually working on his PhD down at University of Alabama on looking at the relationships between swine lagoon locations and socioeconomics in the state. Really kind of neat project, to be honest with you. And he did some really, really interesting things, to be honest with you. I can show might have posted his exam, but these are the swine lagoons located in the state of North Carolina. So as you can guess, we're probably looking at like the spatial mean, spatial median, centrality metrics of the swine lagoons compared to the center of the state. Where in words can you tell me are most of the swine lagoons? East. Okay, so when I run spatial mean or spatial median or central feature, where do you think it's going to be? Probably somewhere around here, right? Somewhere. I don't know exactly. It might be over here. It might be here. It's not going to be over here. Okay. Other thing is Forsyth County. Does anyone know where Forsyth County is? And if I really wanted to know, these are some tricks and tips that I've got. If I can right mouse click and I can click on label features. But this is Forsyth County. Do you see any points in Forsyth County? How many swine lagoons are in Forsyth County? What's the density? 0. You got 2 answers I just gave you, okay? So when you run that spatial join there, don't make it more difficult. I was just talking with Josh about, kids who bang their heads against the wall saying, I can't figure out how to find, just look at 0, okay? Because when you run the spatial join, it might give you like a null. It says no. Null is another fancy way of saying 0 in this case. Okay, so make sure we understand what the computer is telling us. Really work smarter instead of working harder. Okay, because there are going to be some tougher questions here with the z-scores and all that other stuff here. So don't bang your head against the wall with some of the simple things here. And really have a good idea as to open up this project. You got this project open right here. Run the spatial joins beforehand. Make sure they make sense. Okay. You should get about a dozen here. You should get 0 here. I'm already giving you the questions. I might change the name of the county or something like that, but it's all the same. Okay. So now when we look at the exam, these exams are kind of, to me, a combination of stuff that stuff that you can apply, hands-on. I really hate the idea of like rote memorization and looking up terms. If we're going to do anything with terms, it's going to be the application of terms to what we're doing here in Geostats here. Hopefully this exam kind of articulates that. So the midterm exam, you can see I'll post the due date and all that other good stuff. I'll also post the procedures for these as well. But this is just kind of what the exam looks like here. I'll post the dates here. Why using this median to describe centrality is better than the mean? Like, what are some things? We've talked about these before. You see this table here. We've got an APRX table for counties. For questions 2 through 13, answer the statistics for median age and average family size. And so we have median age, min, max, mean, median, range, standard deviation. Do we know how to get those from one of the columns? I hope so. Right mouse click statistics. We've got everything right there because you're going to need that mean in order to calculate the z-score. Okay, so you'll need that mean in order to calculate the z-score. So what's the minimum for the attribute minimum age? What's the maximum? What's the arithmetic mean? What's the median? What's the range? You know, if you forget about that statistics, at the very least, you could sort them, look at the top for the lowest, look at the bottom for the highest. Go, all right, let me look for the two middle ones. You know, if you scramble, but I'm not going to go through and make you count and look all these things up. So there's going to be a tool there available for you in order to do all these. What's the standard deviation? What's the minimum for average family size? So these are some basic descriptive statistics that you're going to go through and answer the table. Now with this, calculate the Z-score for Durham County, Forsyth County, and Allegheny County. So Z-score, Durham County, Forsyth, what's the little formula here for Z-score? I'm going to point this for everyone. What's the formula? We want to calculate Z-score equals what? What's that? X minus the X bar divided by this thing here. All right, what's this thing stand for? Standard deviation. Where do you get that from? Statistics that you calculated in the previous question. What's X bar stand for? Average. Where'd you get that? Previous question. Now, $1 million question is what's X? The value for whatever county, Durham County, for what? Median age, or whatever we're looking at. So you got to go look at median age for Durham County, subtract the average, and divide the whole thing by the standard deviation. Because remember, Z-score is what we call a local metric. Local, meaning the Z-score for Durham County is going to be different than Nash County, which is going to be different than Forsyth and Allegheny County. Okay. Now, there's lots of ways you can do it. I just kind of put this in Excel so you can do the calculation. So you've got to do a little formula right here where, all right, you can do the X, then you can put the X's next to it. You can put the median age for that particular county. You can do it in ArcGIS Pro or, God forbid, just calculate it by hand. Yeah. But I put this thing here so it could just be organized so we can just plop it right there and look at the answers. Right, so it's relative, you know, this is like last year, probably the first year I kind of did all these here just to make your life, not make my life easier too. You know, make my life easier. So you can use calculations if you want to, you know, and just do the calculation because for every calculation, the average and standard deviation, if it changes, there's going to be that. So you might want to put a column that says this is the median age, but these are the Z-scores. For these. Now, what are the Z-scores? A good Z-score goes from what? -3 to about 3. You know, you get anything wacky, your math's wrong, or you brought in the wrong average, the wrong standard deviation. Even for things like median age. What should the average median age for all counties be in North Carolina? Should it be 80? Should it be 2? Somewhere in between. 40, 41, 42, something like that. You know, because, you know, if you're going through and you're transposing the standard deviation and the average, you get numbers that don't look right. All right, so make sure you check yourself on this. Okay. I don't want to give away the whole exam here because we can just go back. All right, so what's the Z-score for median age for Durham, Forsyth, Allegheny, and then the Z-score for the average family size. All right, I got the Vikings and the Nighthawks, the average number of wins here. So we can see the average number of wins. What's the range? Okay, and we're not going to calculate, but a range is what? One number, high minus low. And that's all it is. So don't give me like 3-17. I'm going to mark it wrong. I'm going to mark it wrong. He's talking to people here. I will mark it wrong. So range is a value. Range is a descriptive metric. Okay. What percentage of wins occurred between 2014 and 2016? How do we calculate the percentage of wins? This one plus this one plus this one divided by the sum of all of them. And guess what I have right here? winds. So I can go to Nighthawks and Vikings and just highlight these in the bottom right. Look what I got. I got a sum of 88. So I don't know if anyone's noticed that in Excel, but in Excel, you can highlight some of these. And I think you can change these numbers as well, but it's got an average of 8, a total of 11, a min of 3, a max of 14, and a sum of 88. That might be the way that I set up my Excel. Maybe I can right mouse click, single mouse click. I don't know. All I know is my Excel does that. I don't know what else is Excel. Okay, but I've got some basic descriptive metrics sitting right there, ready for me to go. So I think this underscores the importance of these and the ubiquitousness of them as well. Okay, so it's the range of winds, what percentage of them, what team had the higher average of wind, which team had the higher standard deviation of winds. Explain something about standard deviation. Okay. All right, next. 25 through 28. I got a sample attribute table sitting right here of county population. What do I have here? This is the population in thousands, or in thousands of dollars. This is the population of these particular counties. And basically what I want to do is, what's the arithmetic mean? Can we calculate the mean of income? You bet. Equals average. What? These things right here. 39. Now, what do you notice about these? I've seen one that has a population of 400 has a median income of 32. What do you think that's going to do to the weighted average? It's going to skew it in a different direction. Because when I average it, basically, it assumes the weights of all of these are the same. And this is what we're going to get into with the exercise. So what I asked for next is, what's the weighted mean? I'll let you all calculate. What's the median? And then, using the data above and the arithmetic mean, what would a county's median household population be if it were one standard deviation below the mean? Okay, what do we do here? Same equation. We got the same exact equation. Okay, same exact equation. But this time, what's z equal to? -1. What am I asking for? X. What's the county going to be if it's one standard deviation below? How do you get the average? What answered one of the questions that was arithmetic mean? How do you get the standard deviation? Go and calculate and use the little standard deviation thing that we did a few weeks ago. STDDEF, standard deviation. So we just plug this. So can we solve for X? So if -1, just say equals X minus, just say the average is, there's no average, 39. 39, say the standard deviation, just say it's. Question. Can you solve for X? Everyone please say yes. Please not approving when we do this from algebra. It's a little tricky. So what do we do here? All that cross, we call it cross multiply budget. -5 equals X minus 39 plus 39 plus 39. X equals 34. Yeah. Okay. Hopefully everyone joining us can kind of see this. That's all that means. Maybe I'll change this number to one standard deviation above. I don't know. Okay, I might tweak these a little bit if I've got some time. Okay, but that's all we do. Okay, you got one equation, one unknown, you can solve it. Okay, in circuit analysis, we've got one equation, two unknowns, so one's going to be dependent upon the other. Okay. Oh, this is from a homework. Okay, we got the APRX file. Okay, calculate, use the spatial join. Calculate what are the number of swine lagoons? So all we're gonna do is just, we got a map right here. Let's run that spatial joint. We did this for cancer rates, right? So we got rate, we did this for cancer rates and then total cancer, patients or whatever it was, deaths or whatever it was we were looking at there. And then we revisited a couple weeks later, look at number of people per, number of deaths per 1,000 people, 10,000 people, something like this. So when we look at NC counties, when we run the spatial join, we're going to get a frequency or something like that. We have a square mile, so we're just going to get that frequency divided by square miles, and we're going to get a density. All right, this county has 4 swine lagoons for every square mile. That's a lot. Sounds like a lot. This one has 0.7 swine lagoons for every square mile. This one has 1. This one, Forsyth County's got 0. Okay, so you can see where we have swine lagoons, and you can see where the concentration of them are. So you're going to do this, and then with normalization, we're going to look at the swine lagoon density. So you got to do one column divided by another column. Okay, if worse comes to worse, what can we do? Hey, I don't know what to do. I forgot how to do this in ArcGIS Pro after my spatial join. What are some things we can do? Hey, copy. Plop that thing straight into Excel and do your calculations from there. When in doubt, and just look for them. Okay, so if I forgot how to add a column in ArcGIS Pro, bring it all in here. Okay, make sure it has that frequency or that count at the end of them, because that's where we get that spatial join from. Okay. So the number of swine lagoons, the density. Okay, last few questions here. This is what we're going to focus on today, but what county is the mean center of population for the entire state? What is the center of, what county is in the center of swine lagoons? What county has the central feature? And then basically briefly describe the spatial distribution of swine lagoons compared to the population in North Carolina. And then we do something with standard deviation ellipses right here that we'll kind of look at for homework. And then we do a new minus old for population change. You know how to do that, right? We did this last week. We did this for homework. So there's a column there for POP 2010. There's a column for POP 2013. New minus old divided by old, multiply the whole thing times 100. And so what county had the highest population increase? What was the range of values that you have? Okay, range of values. All right, this is tough. Yeah, I'm not kind of joking here, but this is tough. Why? Because do you think you're going to have negative population? Do you think you're going to have any negative values for population change between 2010 and 2013? Yeah, you're counties that went down. So if I have a range, if the lowest is say negative 2.3 all the way up to 5.7, what is the range of values? The range of values, high minus low. 5.7 minus what? Negative 2.3. This for math class. The range is 8. Yeah. So in reality, the range is the absolute value of the difference. Because if I were to just do it the other way around, absolute value makes it possible. Okay. I guarantee someone's going to get this one wrong because they're going to go through and do these great calculations and then just subtract one from the other and get a range like 2.4, even though we know that it goes to the negatives right there. Okay, those are about the values you should get. What type of population increase? Should counties double in population over a period of 3 years? Okay, no. Okay, so get an idea as to what a good answer looks like. All right, range of values. How many counties had a population growth less than 0? Can we do that? We could do a query. Give me whatever column you call it, top change less than 0. Okay, so we can just kind of go back to right here. Now this is kind of real old school, but select by attributes, top change less than 0. Let's give them to me. If need be, just sort them and start counting the ones that are less than 0. I have a little negative sign next to them. Okay, what's the average for all population change that you computed? All right, so, all right, that's the quiz or exam. Okay, I believe it's worth 100 points. So of the 500 points in class, it's worth 20%. And so it's kind of a real good selection of, it's a good summary of some GIS skills, some geostatistical skills, some just, hey, just go and calculate averages in Excel and a little bit of the weighted average stuff. All right, next we'll look at the homework here. So homework. Exercise number 4. All right. All right. So I got a video here. According to the global and descriptive statistics, what's the difference? And I think by this point in time, what's the difference between a global statistic and what's the difference in local metric? What's an example of one local metric that we've talked about? What does the word local mean? To describe a particular record, and eventually it's going to describe a particular enumeration unit, point or polygon. Or that descriptive describe the entire data set. So for median age, it's got a median mode that describes the entire median age, where that z-score is going to be unique for each county. So Durham County will have a z-score that's different than Allegheny County, which is different than Guilford County, which is different than Forsyth County, which is calculated using the same exact median age or exact same mean and standard deviation. Okay. Because z-scores are local and globals are going to get big when we start in 3 weeks, because in 2 weeks we'll take the exam and we'll talk about the position paper. And then in 3 weeks we'll start talking about, we've got quadrant analysis, inferential statistics, and all these other things. So we're also going to have this global, local as well. So when we open up homework number 4, what county is the median center of population of counties? Okay. Now, when we open this up, and I think we'll just start the homework. How's that sound? Because I think we still have an outstanding reading due in a couple of weeks, right? So we still have a reading due. Those readings are pretty tough, isn't the right word, but they're particular. You know what I mean? And they're kind of particular after the fact, because I kind of know this. I know this stuff pretty well, so I want to, and the wording was very particular as well. So, okay, so we're looking at these enumeration units here, and I've got counties. I've got block groups right here, if you could check these, and then I've got blocks, and I've got blocks, and basically we've got counties are divided into census tracts. Census tracts are divided into block groups are divided into blocks. And basically when they collect the census, so we can get people by block, typically like socioeconomic indicators like income are not collected at the block level. So we just know how many people live here because I can cross-reference block level data and figure out, that's you and that's you. And who you voted for, or whatever. We're looking at like voting statistics with some of the things that Dr. McGinn does. Okay, so we've got counties right here, and we're also looking at deer vehicle collisions. We had a student who attended NC State, and he now works as an estimator for I think landscaping company, but he did a lot of like property mapping and was, doing GIS. His name was Eric. And so he wanted to do something with ecology, with looking at the relationship between deer vehicle collisions and other indicators, more natural indicators like what is the population density and all those other things. So we got this data set here. Basically, what do these points look like to you? They're just a bunch of points, right? That's all they are. You know, it's difficult to make any sense of those. So what we're gonna do is, we're gonna calculate the mean center of population at the county level. And then we're gonna do it for different enumeration units for blocks. We're gonna do it for block groups, and you're gonna see what happens to it right here. Now, we're gonna calculate the mean population center of all of these counties, okay? And we're gonna go and open up a tool because I think that's the second question here, and I want to make sure. So using the data, what county is the mean population center of counties? Because we're gonna do the center. What county is the mean center of block groups? And then what county is the mean center of blocks? So we're gonna calculate these at different units because it's gonna use the center and then calculate the weighted average of these 10 block groups. So when we open this up, we're going to click on analysis. We're going to click on tools. And I've shown my other group this before. When we go to geoprocessing, I've got favorites. So you can see some of the tools that I've worked with before. And now I've got toolboxes. Like I've said, I probably use maybe half of these toolboxes. These are all the different toolboxes available to you in GIS. And so we've got students, you know, and some of our students, all they do, they live just in utilities. That's all they do for a living is just become expert at utilities. Space-time patterns, you know, that wasn't around when I was doing stuff. Aviation tools, indoor tools. So there's a lot of really neat tools out there where you can make a living and just live in for your entire existence. To me, what we're going to look at are, we're going to look at spatial statistics tools. So we got patterns, clusters, measuring geographic distributions. And so we're going to look at measuring geographic distributions. So we're going to click on spatial statistics. This is where we're going to work right here for this class. If you take raster GIS, there's a class called raster GIS being offered next semester, I think, by Dr. Malhotra. I think you're going to be living in spatial analyst. And students that I was just working with, we did something in spatial analyst where we did interpolation, which isn't quite a statistical tool. It's like a numerical calculation. And look what we have here. Central feature. Oops. Central feature, mean center, median center, neighborhood summary statistics. I don't even know what that means. I could probably take a good guess at what it is, but I don't even know what it is. And these are all new tools that are being added. And then the standard deviation, standard distance, which is your standard deviation ellipse. Okay, so what I'm going to click on here is my mean center. When in doubt, you can click the little question mark sign and it opens up about how the mean center works. So you can see input, output. How does the mean center work? All it does is just average everything up. And then the weighted mean center is the same exact thing. It's the weight times value divided by the sum of the weights. And maybe if I have a chance, I'll kind of write that out, write out that calculation. Hopefully it's going to make sense to everyone here. But when in doubt, just click on the little question mark button, up pops up something that says what it means. Okay, so my input feature class is going to be what? Counties. Output feature class is going to be week 5 counties, mean center. And I'm just going to give it the name of counties. And my weight field is going to be top 2013 because these counties aren't going to be the same. What if I were to leave it blank? What would the average be? What's the weight of each one going to be if I leave it blank? They're going to be the same. They're going to be 1. Just like us averaging up all your grades, do you want to average up the A, B, B, C, C if the C's are 1 credit class and the A's are 4 credit class? You bet you don't. You want that weighted average. And then we're gonna do pop 2013. I don't really do case field. I don't do dimension field, so I haven't had a reason to. Cases, I think you can set up like if statements within it. But I'm gonna just click run. And you know what? I'm gonna keep this tool open while I'm here. Now, what's this green dot mean here? What's that? It means center. And just for the heck of it, just for the heck of it, this is the unweighted, this is the weighted. Why are they so different? Where's the population of people, large population of people in this area? Here, here. So it's gonna move it in this direction. So basically what we do, basically calculate the center. So it's hard to figure out the center. It calculates the center of each one and weights it. So your X is gonna be what? X is gonna be X of 1 times top of first county plus X of 2 times the top of the second county plus X of 3 times the top of the third county, all divided by the sum of the tops. Done. Okay. Now, how many calculations did it really do? How many counties did it have? 1, 2, 3, 4, 5, 6, 7, did 11 or 12 counties. Now, what if we do it at a different scale? What if we do it for the block group scale? Do you think we're gonna get a slightly different answer? Bet, because instead of doing 12 calculations, it's gonna do however many block groups there are in this area calculations. What county is it in? This is Guilford County. Now, it definitely moved a little bit. And basically, some of the questions I have below are a little bit more interpretive, meaning like, why does the center keep moving if we're calculating the same exact, we're doing the same exact calculation every time? Why does it keep moving? Why do these centers move every time? Because we're using slightly different data we're using different enumeration units of the same data. I bet you if you were to add up the population for the counties versus the block groups versus the blocks, it better add up to be the same thing or close to the same. So I'm going to keep this tool open, just like I do with my query editors. And this is for the people here joining us online. You can see basically what that weighted average looks like. So you can see what that weighted average looks like there, what we did just now. Now this time, instead of counties, I'm going to do it with block groups. And I'm going to weight it by pop 2013. Okay. Did everyone see what I did differently? So now my input is going to be what? Block groups, the weight fields pop 2013. I give it a brand new output feature class. You get something that's going to appear that I can kind of recognize it. You know, because if I wanted to, look what I can do. You know, properties. You know, I can change it from, there we go. So we've got the unweighted one in pink. We got the weighted at the county level in pink. Let me go back to I got the block groups at the center of block groups here. So what happened, when I group it at the county level, it's here, at the block group level, it's here. You think it's gonna be different for the block level? Yeah. Why? Because we're doing a lot more calculations at the block group level. We got X1 times the top of X top 1, X2, X2. How many block groups are in this area? Probably 1,000. Instead of 12 counties, we're using the centroids of 1,000. So it's going to be quote unquote better. A little bit better. So briefly explain why the mean center of population from using the block groups has changed. And then in what county is the center of blocks? You can go through and calculate that. We're going to use POP 20 for blocks because block data gets really big really quickly, and it's really hard to find the GIS data for it because they typically only collect like population for. So this is for blocks. These are the block groups, and then these are the blocks. Like literally, these are blocks. So this is what like block level data looks like. 42,000 blocks here. You can see housing units and POP 20. And you can see, some of these blocks go from about 4,000, 3,000. We got a whole lot of zeros right here. And so when you calculate the mean center of population using block level data, what's it going to do with those zeros? Are those zeros going to be counted at all? Are they going to be counted as all? So it's only going to calculate those which have population because it's got latitude, but it doesn't have population. So that weight is going to be what? 0. Doesn't have a weight. It needs to have some sort of weight. Imagine taking a 0 credit class. What is that going to do to your GPA? Nothing. Nothing. It works the same exact way. Okay. So that's how we can kind of express. That's how we can kind of express or think of weight. Okay. All right. Compute the standard direction distribution. This is basically what I used to call the standard deviation ellipse for deer vehicle collisions using an input parameter of 1 standard deviations. How many counties does a resulting ellipse intersect with the study area? Almost done with the homework here. Okay. All right, so what we're going to do, let's get rid of these things here. Let's get rid of these. Okay, so basically what I want to do is create a standard deviation ellipse that's going to be located around the mean center. So where do you think the center of this ellipse is going to be? You think it's going to be over here? No, it's going to be somewhere where those dots were appearing when we ran it. And if I had to guess, no, I'm not going to guess. Okay. Nope, I'm not going to guess. But if I were to calculate the mean center for this data set independently, then guess what? That's going to be the center of the standard deviation ellipse. Now they call it a directional ellipse or something like that. So let's go check that out. All right, so over here, let me go back instead of mean center. Directional distribution, standard deviation ellipse. So I want to find the standard deviation ellipse for my deer collisions with an ellipse of 1 standard deviation. Should I put a weight there? There's one. How weight are these deer vehicle collisions? They just represent the same thing? Yeah, they do. I can't say, and if I looked at the data, I would say, hey, this is a bigger deer versus a smaller deer. They're not weighted that way or anything because I don't think I have that information. It's been a long time since we worked with this data set. So there's no weight field here. Let's run this thing. Here it is. What's this mean? Means that here's the center over here somewhere. How many near vehicle collisions are in here? About 67, 68, something like that %. Okay. If I were to get another data set where it's smaller, we would know that it's more, this is more dispersed than the other data set. More dispersed. How many counties intersect with them? Okay, all but one, but let's go through and run it because you're gonna have to do this next week. But I just want to make sure everyone knows how to do it. So now we're kind of starting to put these things back to back on each other. So just for the heck of it, even though I know that, what's this last question ask? How many counties intersect with this standard deviation ellipse? Okay, so I'm going to go to select by location. What do I want to find? I want to find all the counties that intersect with this ellipse thing that I created. And how many of them are there? Just for the heck of it. You can see there's 11 out of the 12 of them that intersect with this ellipse. Now, do you think you're going to have, when we start looking at swine lagoons and counties in North Carolina, do you think you're going to get that answer? Probably not. Okay, so you can see 11 out of the 12 counties. So as you can imagine, guess what we're going to be doing here? You're going to run a standard deviation ellipse. Where do you think this? You think the standard deviation ellipse is going to make its way over here anywhere? No, especially if it's only accounting for about 2/3 of all. So it's going to be probably somewhere around here. And so of the 100 counties, we're probably maybe looking at 20 of them. I don't know the answer, to be honest with you. All right, so does everyone know how I got the standard deviation ellipse we should have, right? But kind of circling back to what we did previously, like the first week of class, we did a select by location. I just wanted to find the counties that intersect with the near vehicle collisions directional distribution. This directional distribution was what we went through the trouble of making using that geoprocessing tool. So that's the resulting feature class of the directional ellipse. So that's the input. So I got to run a directional ellipse and then bring it into a select by location to figure out how many account for that. Just by looking at it, you can see 11 out of the 12 intersect with it, but this might not be all that easy when you do it for the whole county and swine locations and all that other stuff there. Yep.
So, if I just actually see the number.
Oh, the number, 2 places right here. One down here under counties, 11 out of 12. Look in your attribute table, and the question was to those joining us online was, how did you get that number 11? And someone just went and counted. Easy enough to count right here. But if you look at the attribute table for counties, you can see them highlighted in blue, which satisfy this select by location. But in the bottom left, you can see 11 of 12. Can you see that? Okay. I think in our rotation, I was looking at like the wrong table today. And I'm like, wow, there's stuff that's blue that should be blue somewhere else. And I was looking at the wrong table. So make sure you refer to the right table here. We're looking at counties here. We're looking at counties. And so we got most of that homework done. We got another reading for everyone as well. And then I will not be here next week. So kind of take the time, take the opportunity to get everything turned in. I'm going to grade everything tomorrow so I can get those off my plate and kind of give you some valuable feedback and timely feedback so you know where you stand. You know, my philosophy with this class, you turn in everything, you do a good job, you're gonna do well. You know, I don't think, I'm not gonna sleep at night, you know, I'm not gonna lose sleep if, you know, someone, does, who turns in everything, who's maybe not great at geostats, I'm not gonna lose sleep at night about that. I'll lose sleep if someone kind of, they don't do anything and they come at the end of the semester and say, I need this, this, and this. I get a little out of sorts with that stuff. But so those of you joining us online or asynchronously, just make sure you stay caught up with things because I take attendance for people who join asynchronously and online through your attendance. And so make sure you're checking in and doing all that other good stuff. Make sure stuff's turned in because the deadlines for the people who meet here face to face are the same deadlines for the people who meet us asynchronously. But the exam next week will, exam in 2 weeks will be given slightly differently for those people who attend this solely online. So be on the lookout for an announcement, and then probably next week I'll send something regarding the exam, and we should be good to go. Give some thought to the position paper. Cameron's got a really good idea. We threw around some things with that position paper to, hey, is there a relationship between income and motor vehicle deaths? That might be something that's easy to do because we already have like where the high deaths are and the low deaths are, just bring it in and calculate those, or we could do a clustering analysis of those. So think about some of the things you want to do. That PM stuff that we're developing. Last week we looked at some of the relationships between we looked at income with the COVID stuff. So, hey, is there a relationship between air quality, high air quality in the, the low income areas? Hey, let's look at the high income, the low income, let's look at the average air quality and let's see if there's some differences. Maybe there isn't, because the highest, poorest air quality was in Durham, Raleigh area right there. But if we look at it at a different scale. So I don't want to waste anyone's time anymore. So if you got any questions, let me know and see you all later. The end.